Sorry, I should just start recording here.
Recording in progress.
So I'm just
Another.
going to record. Yeah, I'm going to record the class just for some people who can't be here or just missed the lesson just cause.
Do they see me
I'll
as well?
upload it. I don't know, maybe, but I'm going to upload it onto YouTube, the YouTube channel. So what I'm going to do is like after post class message, and I'll put the stuff here, like say for example the notes link, and I'll also put a link to the Zoom recording as well. Okay, so I'll populate that after class, but I'll also send everyone an email as well so you don't miss out. Cool.
100%, sir.
I'll also put up homework as well. So those are the areas that I'll start filling out as well. Okay. So I'll share my iPad screen now, just so you can get a feel for it. What the hell is that one?
Oh, is your iPad in Zoom?
Yep, I'm gonna share it now. Shit. Give me a second. There we go, much better. Okay. 1, 2. Yep, just rearranging some stuff here, so bear with me for a second. Okay. All right, so linear growth and decay, this is what we covered last lesson. Could you please recall, or someone flick through their notes? I want you to pull up that PDF note from our last lesson. I'll give you some time to do this. And I want you to give me the formulas or the equations for a linear recurrence relation. And a rule for the linear terms, for the nth term. So once you have it up, can you please shout it out?
I'm going to be quite frank with you. I haven't started AD.
Yep, that's fine. You can do that for homework. All right, let's have a look back here. Can anyone see where the recurrence relation is?
Vn equals Vo plus Nd.
That's correct. And that's our rule there, or that's our little, that's our little rule there, or our equation. What is also included with our recurrence relation? Same person can respond.
So what's wrong?
We have a rule here, yeah? What else is included with it?
The starting point?
That's correct. The starting point. So I'm going to take this here. I'm going to pop it down here below, just as revision, right? Because we need to know what each of these components are. We've got our starting point. We've got our rule or our formula there for the recurrence relation to find the next term. So this is the next term. and we have to use our current term that we have. Notice this plus D here. We also need to find out what this plus D is, okay? And that's a separate calculation in and of itself. So you need to run this calculation on the side by itself, and then you can go ahead and you can fill in the rest of that, okay? Now we also did the rule for the nth term, and this is all linear stuff, yeah? The rule for the nth term, if we scroll back up into our notes, and I strongly suggest you to find it and write it down, yeah? There's two different versions here for the rule. And I think there should be two different versions for there should be two different versions. Oh, whoops. For the recurrence relation as well. I might put this down here actually, so you can see them. I really want to put it side by side, so you can see it for comparison. Notice the features here. Each of those features have different components, but the way that you calculate D is still the same across both of them. Now this here could be either a plus or a minus, okay? One or the other, it can't be both. In what cases would it be a plus?
When the rate is like going up?
Yep, so which scenarios would that be for? You can type it in the chat if you want. I'll wait.
Investment, probably?
Yep, what kind of investment for this one?
So is that compounded?
This is linear. Linear recurrence relation, linear growth and decay. Compound is with geometric.
Oh.
So what kind of investment would this be?
Would it be like simple interest investment, probably?
That's correct.
Okay.
So it'll be an investment, but more specifically, it'll be simple interest. What happens if it's a minus?
It would be a depreciation.
Yep, what kind of depreciation?
Linear.
Yes, it is linear, but there's two different types of depreciation that we learned about in our last lesson.
Flat rate depreciation.
Yep. And what was the other one?
Unit cost depreciation.
Yep. The other one was unit cost depreciation. So can you explain the difference between the two? Yep, I hear some people Googling. That's good. If you don't know, Google it.
Isn't flat rate like going down at a constant rate.
Yep. So same amount every year.
Unit cost is like the
Exponential.
value of an item is reduced based on how much it is used.
Yes. So does it go down by the same amount every year?
No, it's
No.
exponential.
Depends on
So
how
it-
much it's used.
That's correct. Depends on the usage. So the more you use it, the more it will depreciate. Does that make sense?
Yep.
I taught a whole lesson on this. Clearly nothing was really stuck with anyone. Okay. So this is a bit of a concern because when we get into the SAC, I will be asking these questions. I will be asking you, how do you know that this is flat rate depreciation? How do you know that this is unit cost depreciation? Because I will present you with a scenario. I won't tell you, I'll give you the numbers and stuff, but then the question will ask you, what kind of depreciation is this? And you have to figure it, you have to decide for yourself, and you have to explain why. The answers are here. I'm writing the answers down for you. And whether or not you want to take this into consideration, or if you want to look over the notes and actually write this into your knowledge books, that's up to you. My question is, do you actually want to write it out into your knowledge book and try to understand what's going on? Or are you going to take the easy way out and copy it down? Question mark. Okay, so please, please, please take that into consideration. Now, what we're going to do is we're going to, oh, whoops. We're going to look at modeling growth and decay using recurrence relations, and then we're going to look at it using rules as well. Okay, so I'll just take it out now directly from the notes, the recurrence relation. And also so this is recurrence relation for increasing and decreasing. And there's special names for each scenario as well. Give me a second. So 8F, you can see here, we actually have a rule for it. So I'm going to put them side by side, and we're going to do a bit of a summary at the end for this as well. There are very, very high levels of similarity between the two. Okay, so first of all, you've got to decide whether it's a linear or geometric growth or decay. So is it going in a straight line? Is it the same amount every year? Or is it compounding? Does it build up upon each other? So that's the first thing that you have to ask, because that narrows it down. After that, you have to narrow it down even further. So if we're looking at geometric, is it increasing or is it decreasing? And are they actually asking us for a recurrence relation, or are they asking us for a rule for the nth term? Hi, Muzzy.
Hi, Mr. Dean.
How are you?
I'm good. How are you?
Yeah, I'm good. I'm good. Welcome to the party.
Thank you. Thank you. I made it.
Or the prison. Yeah. I'm glad you made it. Sweet. Where were we? Matt, I've got a question from you. For flat rate and unit costs, can that be used for appreciation as well? No, usually for flat rate, well, simple interest is a flat rate, yeah? When we talk about depreciation for flat rate and unit costs, that's just for depreciation itself, okay? So those two specific ones would just be depreciation. So I'll grab both of the titles from each of those exercises because we want to kind of have a look at this side by side so we can compare and see the similarities between them as we do our examples. So bear with me for a second. Now, if we have a look at all of these in together, we can draw the similarities for the recurrence relations, and we can draw the similarities for the rules for the nth term, okay? If we have a look at these variables here, let's break it down. It's very similar to when we had linear growth or decay, okay? So for a recurrence relation, when it's geometric, you start off with the initial value or your starting point. We'll call it the starting point. Can anyone tell me what this Vn plus 1 is or what it represents?
Next term.
The next term, correct. So I'm just going to label that there, the next term. It will equal to our current term, but instead of being added by a number this time, it's going to be multiplied by a number instead. So,
Sir, my internet was shit.
yeah, all good.
I drove back.
All right, thanks, Coda. So if you have a look at this R value here, we have to ask ourselves, what does this R represent? Or if we have to do a separate calculation for this R value here. There's a name for this R value here that's not mentioned in the book itself. For the D, we called it the common difference. For this one, we call this the common ratio. So let me just label that. That's what the capital R stands for, the common ratio. Now there's a way for us to calculate this R, and you would have to go to a side to do a separate calculation for that. The R value will be equal to 1. So 1 whole plus the rate that you're looking at. It could be either a plus or a minus, okay? And so what we can do is we can look at the scenarios when it's going to be a plus or a minus. Just looking at this little summary at the top here, if you can see it clearly, I hope you can. In what scenario would it increase?
With appreciation.
What kind of appreciation?
compound.
Yep. So how is it appreciating though? What are you putting it into? Can you give me an example of?
All right, let's say you put it into a stock or like a cryptocurrency, yeah, the usual. It doesn't go up at a constant rate, so the cost of the currency goes up exponentially. Doesn't go up in a linear trend. That as it goes up, so can your investment as well. So let's say I put $10 into a stock, and it goes up. Let's say one day 3%, next day 2%, and like constantly different numbers. That would be exponential growth.
Would it be exponential growth if this value keeps changing?
No, it would be geometric.
Well, the thing about this is that the scenario that you're presenting, the amount that changes every day either goes up or down, right? Up here, when we're looking at this idea of investment for compound interest, we only want it to go up. Now, the thing about stocks is that it's unpredictable. It can either go up one day or it goes down the next day. With the investment for compound interest, we're just looking at the basic formula where it only goes up, okay? So in this case, it only goes up just for compound interest. And so say, for example, the scenario here would be that if you put this into your bank account, or let's say you put it into your bank account, a savings bank account, and the bank account says every year you're going to get 2% interest. That's compounding interest right there, and it will build on to the amount that you currently have in your savings. So that increases based on what your current is, and then it builds off that one. And so it goes up further and further. We'll look at the numbers later, and we'll play around with the numbers just so you can see that the interest that you get in between changes, okay? Whereas if you look at simple interest, the interest that you accrue every period is the same, okay? So that's the one for compound interest. It increases, it only increases. So you got to be careful about when you're talking about stocks, because that can increase or decrease. It's unpredictable, yeah? We want something that's stable. Now, for this depreciation part, in what scenario would we have for this one here? It's depreciating, but what kind of depreciation is it?
Unit cost.
What's that?
Unit cost.
Unit cost? Does it mention unit cost up here?
Isn't it balance depreciation?
Yep, it's actually called reducing balance depreciation. Reducing balance depreciation. So say, for example, you take out a loan from someone, or you take out a loan from the bank. What's going to happen is that they're gonna make you pay off this loan. But every time when you pay off the loan, they calculate a bit of interest, and then you have to calculate it down. You have to cut it down. Then you pay it off slowly. Okay, so we're not looking here at when you pay it off and then you take it off. You're just looking at it as it decreases. So another example from this one here, or perhaps a better example than a loan from a bank, is if you purchase an item, like say, for example, if you buy a car and it depreciates by reducing balance, depreciation. So it will decrease the value of the car. The more you drive it, or after every year, it'll just decrease more and more and more in its value. Okay, so that's why you see like really old models like of cars from like the year like 2000 or 2010. You'll see that on like a car sales website, it might only be a couple of $1,000. Yeah. So it depreciates in that particular way as well. So this is for a geometric recurrence relation. What's the next exercise focusing on? I'll make this smaller for now, and then I'll make it bigger later.
The rules.
Yep. So now we're looking at geometric rules for any term. So remember, just like the one in our linear growth and decay, this one only takes one step at a time. Whereas this one here, we can actually skip to, say, for example, the 40th term, because otherwise you'll sit there and you'll spend your time spamming the enter button on your CAS calculator. So this gives us a way for us to jump terms and just pinpoint it straight to the one that we want. So rules for that's why they call it the nth term. This n here can be any number. That's what the n stands for. The rule for this one builds off the recurrence relation. And instead of Vn plus 1, which is the next term, building off of our current term, we would have the term that we want. So Vn, which is any term, it would equal to our common ratio. But this time it will actually be raised to the power of n. And when we multiply it, we multiply it by our initial value. Okay, so if you have a look, if I take this little r here, we know what r is. R is the same as it was in our previous example. But if we take this idea now and we all put it together into a particular form, I want you to see if you can recognize where this is coming from. So we've got this r here. We know that the r is 1 plus or minus this r over 100. Let's just focus on the plus 1 version for now. So instead of writing r, I'm going to write 1 plus r over 100. I've taken this definition and I've substituted into there. This whole thing is raised to the power of n. So because there's two terms, I need to put a bracket and I need to raise it to the power of n. Are we starting to piece together where we've seen something like this before?
Yeah.
Yeah. Where have you seen this, or what is it? Can you identify it?
Part of compound interest.
Compound interest. That's correct. So notice here, instead of writing times V0 at the end, you would have had times P at the front. So it's very much, so this Vn here is just the amount or the value of the investment after however many years or however many periods. So you've seen this before. It's just that in year 12, because remember, this is year 12 content here. In year 12, they just simplify this down to that particular form there. So it's much more simplified and you break it up into 2 bits rather than having it all in one. Okay, so it's not like you haven't seen this before, you have. I'll just write it in terms of, the other structure and I'll write it in the same format, okay? So when you look at it, you can see and compare between the two, like so. Okay. Now this plus and this minus, once again, we're looking at compound interest for loans and investments. By the way, I believe that for this minus here, there would be another scenario. It would be for a loan as well. Okay, so if you take out a loan from the bank, yeah, it would be depreciating. Yeah, investment on loan would be a plus. Sorry, it's not depreciating. Let me just blow this back up. So these plus and this minus here actually holds true for both the rule and the recurrence relation. So whenever you see that plus and that minus there for geometric growth or decay, it will be based on that. These two or three scenarios that I'm going to finish writing up. Because a loan also accrues interest as well, and it would be compounded. So let's actually take this knowledge now and we'll apply it to some examples that are in the textbook, okay? And this should assist you with looking and breaking down each of these questions, because this is actually really, or well, not really, very, very heavy in terms of content and wording. And the fact that I'm trying to jam it within the next, let's say, half an hour or so, it might seem a bit rushed, but this is why we're recording this, so that you can go back and you can watch it and skip and zoom back to the parts where you need to have a listen to again. Okay. So this first example here, I want you to identify what we're looking at. Are we looking at a rule, or are we looking at a recurrence relation? And I want you to take some time to just read this. So I'll give you a minute or so to read this and see if there's any, see if you can write a little summary for the information, just for this section here. I'll give you a clue here. Before we even write down this one here, we should start off with the template, okay? So the template, or the formula itself for the recurrence relation, was written before. So I'll start you off with this. What I might try doing as well is I might type to the chat. So you can type and respond in the chat as well, instead of me asking a question. I don't like running polls because it's just, it makes the screen jump. So I'm gonna type in the chat here. So what is the, whoops. What is the value for V0? So that V underscore 0 just means V0, yeah? The underscore there means that it goes down.
2000.
Yep. Type it in the chat. So I guess this gives you an opportunity for everyone to answer if you just type into the chat. Thanks, Suma, that's correct. So the next question is, what is the value of capital R? Type it in the chat. You can just type in the number. We're looking at the capital letter, yeah? Not the lowercase one. That's correct, Teresa. That's correct, Uma. Yep, but can you actually see the actual value there? So you could have gone for this one, but I'm asking for the value, yeah? So you could have made the substitution here, but I'm looking at this section up here at the moment. What would your capital R be? So far, Teresa and Uma's got it correct. Well, let's try again. That's correct. All right. So if you have a look at the recurrence relation here, the R value is what's being multiplied with your Vn. Okay, as you can see down here in the template that we've used, that Vn there is being multiplied. So the R at the front, that's the value straight away. You can see it, which is 1.075 times Vn. And so what is your little r then? Type it in the chat. That's correct. Boss. So instead of writing little r equals, I'm just going to place it into the formula here. Yeah. Should we write the percentage sign or should we write just the value? Should we include this percent here? Just the value. Fantastic. Okay.
Because you're already dividing it by 100.
That's correct. It makes it look messy. Well, the percentage sign is already taken care of when we divide it by 100. All right, so we've got all our pieces together. If you actually type this section into your calculator, what value should pop up? If you type that into your calculator, what value should pop up? You type it in to your CAS. Just play around with it so you can actually see what value pops up. And that way you can make that connection. Bear with me for a second. I just need to get my CAS up and I'll actually do a screenshot of it as well.
So
Yes, Matt?
let's say we're in like a test here, or like you give us a hurdle task. We got like with a similar question like this. Do we have to write the part next to it? You know how you write where r equals 1 plus 7.5?
Yes, please.
Oh, okay.
Yeah. So if you type it into the calculator, you'll find that 1 plus 7.5 over 10 over 100 is equal to 1.075. Okay. Yep, Uma, you typed that perfectly into the chat. So thank you for that. So that is this calculation here. And that's why you can see that R is 1.075 in the recurrence relation. Now, that's the first step. It also says here, but I guess what we should also do is understand what's going on here. So what's our scenario? What's actually happening here? It says the following recurrence. Yep, go for it.
No, it's just showing you compound interest. It's just asking you the rate.
That's correct.
I mean, and like the investment.
Yep. So that is something that we should underline. Now, in terms of transitivity, if it's our process, our participant, or our circumstance, which one of those would it be? Is it telling us to do something? Is it a process?
Not yet, it's just stating something.
It's just stating something. So would you call that a participant or a circumstance? The circumstance is if it's telling us how to do something, yeah?
Oh, participant.
Okay, so this is just telling us what it is. So the color coding for it would be in red, okay? All those pieces of information there would also be red or part of the participant as well, because it's just part of all the information that's been given. Okay, so when you can identify this, it helps you break down the question to what you're focusing on and what you need to do. There's actually a word for this whole section here. We call this here preamble. But within the preamble, so it's just like rambling on about a scenario, but within this preamble here, we can also have valuable pieces of information as well. Now, if we read the next sentence, it says in the recurrence relation. So this is what it's referring to. It's referring to that recurrence relation. So that's a participant. What is it when we say VN is the value of the investment after N years? Is that a process, a participant, or a circumstance? Just take a stab. It's 1 out of 3. You can narrow it down by process of elimination. Just type it in the chat. Circumstance, I've got a circumstance here. Mr. Musgrove, what do you think? Is it a circumstance or is it when we look at this sentence here? Because after a number of
Your mic's
years.
muted, sir.
I'm on mute, of course. It would be it's another participant group, so it's another noun group there.
Yeah,
So
because it's not
if
telling
I
us how
was-
to do something, yeah?
No, so if I was looking at this, I'm just going to draw on your screen now.
Yep.
Oh, hang on, look at that. Is actually the process in this sentence, and it's a relational process. It's not, and then that is a participant group, and that is as a noun group as well. They're noun groups.
Oh, okay.
So VN is, it's one of those, I keep calling them relational processes, but they're not. They're irrational, or they're, oh God, I can't think of the name for it. Anyway, but the is what it's referring to, that something is something, you know what I mean?
Yeah. So
And
it's
so
a
that-
process. Okay.
Yeah, the is actually the process, and the other two are part of the noun groups.
So in this first part of the sentence here, would in be the process as well?
Yeah, that's all part of the noun. No, that's just part of a noun group.
Oh, okay. So that would be part of the noun group as well.
Yeah,
All
that's
right.
just, yeah. So the whole first bit's red, and then the is green. And it's not going to be hugely helpful there.
Hmm. Okay. Sweet.
You could almost make that bit blue at the start, actually.
Oh, okay. It is. Oh, it's because it's what we're looking at. Yeah.
Yeah. So VN is the value
Yeah.
of investment after n years in the recurrence relationship.
So we can put that at the start or at the end.
At the end, yeah, you can move that to the start and the end. Just
Okay.
talking about the is there.
Hmm. Awesome.
It's weird. It makes it really weird when they use is as the process.
Okay. So breaking down that question there to understand what we're looking at. Okay.
And then here, you're using that
Use?
relation.
Yep. And the process would be to find.
Yep.
And the participant would be the value after 1, 2, and 3 years. Okay.
Because the
All right.
using is the recurrence relation is how you're finding it.
Yep. It's a circumstance. It's telling us what to use. Yeah.
Yeah. So you could say find the value of the investment after 1, 2, and 3 years using the recurring relation, the recurrence relation.
Yep.
Would
So I
make
can
sense
put that
to
at the end. Okay. Sweet. So for part A here, what kind of values are we looking for? If we want to name it in terms of V.
V1, V2, and V3.
Yep, that's correct. But what do we start off with?
V0.
Yeah, we start off with V0. Sorry, this should be an equal sign. So we start off with V0 equals 2000. And then after that, we need to find V1. We need to find V2. And we need to find V3. So V stands for the value. So the value, what this reads here is the value after 1 year. If we want to read the second one, it's the value after 2 years and the value after 3 years. I've just put it for 2 examples here. So you can understand what the letter and what the number stands for, okay? But now we need to actually use our recurrence relation here in order to work it out. So we've got our recurrence relation here. We don't have to look back up at there because we've already done a summary of our information. And this is what you would write in your books. remember, this here represents our next term. And the Vn here represents our current term. So with that knowledge, if you want to find V1, what would that's the next term. What is your current term then in relation to that?
2000.
2000, that's correct. So you would take, you already have the R value, which is 1.075, and you would multiply that by V0, which is 2000. Okay. So I'll write that in two sections so you can see how it evolves. Sorry. Instead of writing V0, you're going to write 2000 now, and that will equate to a certain number. So you can run that calculation on your CAS. So the value here on your CAS, if you punch it into your CAS, would be 2,150. Then if we want to find out our next value, which is V2, which value would you use for your current term, Vn?
Then you'd use 2150, 2150.
Yep, so you'd use V1, which is 1.075 times this value up here. So that's 2150. Punch that into your calculator. But let's go over to our CAS here, and we'll actually have a look at how we do it. Okay. I'll share the CAS. So we always start we write down our starting point first, which is 2000. And then we multiply, we type out our R value, which is 1.075. That's part of the recurrence relation. And we multiply it by our previous term or our current term that we have. So what would we use? Do you remember what we used on our CAS to get this number here? What would we type into the
times
CAS?
answer. So control negative.
Yes. So you can see the answer on top of that minus button. It's in blue, which means that we need to click onto control first. Then we put the minus. It will pop up the answer. And then after that, what I like to do, just to be safe, because this is compound interest, there will be decimals. I like to approximate the answer. So I'll press, instead of just spamming enter, I'll press control enter. Do I go one more or do I stop here?
You're fine.
Yep. So bear with me for a second. I'm just going to copy this. Go back to the CAS. I'll go back to the iPad. So you can see what's been written on the CAS calculator, okay? So each of these parts here represents your values. So you start off with your starting value. This is your value after 1 year, your value after 2 years, and your value after 3 years. So now we can just fill out these values here, but you have to be careful though. Just because you have it on your calculator doesn't mean that you actually have it on your piece of paper. On your piece of paper though, you still have to show the working out. So for this next line here, for V3, it would mean that you have to take 1.075 times your second term the value after 2 years, and then you replace the number. Okay, so we've got 2311.25. Then you can copy down your answer, okay, which is $2,484.59. So see that what they're doing is they're wanting us to calculate it step by step. Now, I'm just going to duplicate this page here. We're going to look at question B now, or part B. So for part B, it's asking us when it will first exceed $2,500. So on our CAS there, I'll go back to sharing the CAS. What we're going to do is we're going to continue to press Control Enter until we pass $2,500. So you can see here, we've already got the first 3 years. So after 1 year, after 2 years, after 3 years, and that's the starting year. So that's 0 years. This is the 4th year. And what do we realize? Have we passed $2,500 yet?
Yeah.
Yep. So that's what we're going to take. Oh, great. It's not syncing anymore. I'm going to get you to get a mental snapshot of that value there. I'm going to hop over here. I couldn't seem to copy it across. Our value after the 4th year, so that's V4, was equal to $2,670.94. So as long as you know how to do that on your calculator, you can now say, and you answer the question with a statement saying, the value of the investment will, and it's important that you don't just write exceed, you write will first exceed. $2,500 after 4 years. Okay, that's how it's done. Now, it says here, they want us to write down a recurrence relationship, or sorry, a recurrence relation if $1,500 was invested at a compound interest rate of 6% per annum. I'm going to let you give this a try. I'll give you about 2 minutes to break this question down and attempt it. It should look something like this. Follow this structure here for this particular question. You'll be able to answer it. So it seems here today, we've taken a lot more time to answer this and to go through this exercise. Exercise 8F will have to be completed on Monday, which means that puts us behind because I won't be present for Thursday and Friday next week. And then potentially all of week 4, I'll be out as well. So we'll be missing a total of 5 lessons there. I'll get started. You see here, this is compound interest rate. So this is why we want to use this formula here. We want to use this compound interest formula. Yep, that's correct, Matt. Fantastic. Could you also put where? Yeah, fantastic. That's the one. All right, everyone. Once you've completed writing this down, you may leave the class. Okay. So thanks for tuning in. We'll see how we go tomorrow because we do have 1 or 2 more classes. And yeah, we'll bank on that one there. Thanks, guys.